we're starting with, we call these kind of puzzle graphs, and it gives you some information about the function, but no equation of the function or anything like that. And you have to sketch a single, so we're not doing piecewise functions here, okay? A single function. And notice that it says function. So if you're ever doing one of these things and what you've drawn is not a function, in other words, it's got like a part like this and a part like that, not a function, you're not getting any marks for that, okay? And it's got to satisfy all these criteria. Now, we've seen some of these in MHF, and we've seen some of these a little bit, I think, as well in this course, right? Where it also might include a limit statement. Limit is x goes to infinity, it equals something, right? Like it could have other parts to it. This one just has some details on the derivatives, really. Doesn't have anything else. It might have intercepts, might have all kinds of different things. Something you want to look carefully at is it f prime or is it f? Because if you get that mixed up, if you do that backwards, it's not going to be correct, right? All right, so let's do this. The best way to do this, anybody have a suggestion on what would be a good thing to do here? Any guesses? I think the easiest way to organize this information is going to be as a first derivative chart like we did yesterday. So you may sometimes have more than the first derivative chart. I don't know why I'm doing this right now. I'll do this after. But the derivative stuff can go into a chart that will probably make your life easy. Okay, so x. And as I look at the intervals, I've got less than -1, from -1 to 2, and greater than 2 are my three intervals. So I'm going to start from the leftmost point of the graph and move across like we did yesterday. So x less than -1, and then at -1. -1 less than x less than 2, at 2, x greater than 2. So the first line says f prime at x is greater than 0 in those two intervals. So what does that mean? Positive. So in this interval it's positive, and in this interval it's positive. And then it's less than 0, which means negative for x greater than 2, so negative. So what does that mean about the function? Same stuff it meant before. If the derivative is positive, the function is increasing. If the derivative is positive, it's increasing. Derivative is negative, it's decreasing. Okay, that was line 1 and bullet point 1 and bullet point 2 summarized. Bullet point 3. Some people don't understand this notation. What's it saying? This here? Yeah, so it's, well, right, for the function, it's saying the slope is 0, and it's saying the derivative is 0 at both of those points. They're equal to each other, and they're both equal to 0. So that's all that means. It's just a quick way of writing all those things are 0. So it's 0 there and 0 there, which means I have a horizontal tangent line and a horizontal tangent line. And then I look at this and I say, it's going from positive to 0 to positive. So that is called what? Huh? Horizontal twist. Very good. And then positive, 0, negative is a turning point with a max. Why does it give me, so that's that one done. Why does it give me this information? It's giving me the y value of the points on the function. So the horizontal twist, which occurs at -1, actually occurs, negative 1x is negative 1, 1, right? It's giving me the y value. And the turning point, that happens when x is 2. The point is 2, 5. Sometimes these functions are going to be very prescriptive and everybody's would look basically the same. Sometimes they can be different, and I think you've seen that before, and that's concerning to some people. They're like, well, how do I know what it does here? Well, if it doesn't tell you, make sure it's a function, but it's up to you. Don't add extra detail like turning points all over the place that weren't given, but if it doesn't say, your graph may not look exactly like other people's or like mine. In this case, I'm going to mark my points here. So I've got negative 1, 1. I've got a point here. And I'm labeling. A big part of all of the sketching that we're going to do is the label. Okay, this is important. And then at 2 and 5, I got a point. That's a turning point with a max. This is a twist. So what does this have to look like? Something like that, right? Didn't give us the x-intercept, so I can't label them. Another question might have given the y-intercept. And again, like we've seen sketching in MHF, all the pieces have to fit together, and if you do something wrong and the pieces aren't fitting, that's a like direction to you that you've made a mistake somewhere. The pieces don't fit, because they will fit. Any questions? Yeah.
Is this a graph of the derivative or the?
No, this is the original function. All right. So this is the handout that you have. All sketches from now on, it'll say it in the instructions, but you have to show the intercepts. You have to show the asymptotes, if it has any. You have to show all critical points and all end behaviors. Turning points, twists, cusps, I don't know why they're not in there. And cusps as well, right? So any kind of critical point has got to be there. And you complete and you fully label. So you label all the different parts. There's sort of different ways you might label, and depending on how messy or neat you are, you might do it different ways, but I'll give you a way that I think is an easy way to keep things tidy. And this is what we're doing for the next few days. We will add on one more part later this week where we can get even more detail. Okay? This is the function that we did yesterday, one of the ones that we did in the work yesterday. So if you want to see more of exactly what's happening here, you can look at your note from yesterday or the note online and see what was happening there. But this part's already done, and the derivative is already done. We did that all together yesterday. Okay? So to save some time, we're whipping past all of that. You probably want to come up with sort of an order that you do things in a way that even a way you organize things on the page, I think is a really good idea, and try to do it the same way every time. You build those habits, it makes it easier for you in the long run. Okay? And it's easier for you to find your mistakes. Like if you kind of do the same things in the same places on the page every time, you will know where all the different parts are if you're looking for a mistake or if you're looking for some details or something like that. Okay? All right, let's dive into it. So this is how I do it. You're given the function. Beside the function, I do the derivative. And I do all of that first. I do all that work and I clean up everything and I factor it all, so I've got all that done before I start getting into the other properties. So this part's done, this part's done. That's what we had to do yesterday to do the first derivative chart. But now I also have to do the intercepts. So how do I do the intercepts? And you don't want to be spending time thinking, okay, how do I do this again? What part? Like if you're trying to figure it out on the test, you are going to run out of time. So you want to just, for this I do this, for this I do this. You just want to dive in and get going on it. Which? The original function. So the intercepts, for the intercepts, I'm working with that guy. Okay? So we're going to factor it. I'm factoring out x to the 2/3, the smallest x. So it's x to the 2/3. And I'll write this out one time, but this is what you need to be able to do. This is x to the 6/3 minus 2/3. Do you understand? Because 2 is 6/3 minus 2/3 is giving me 4/3. Again, this is a little bit outside probably your comfort area, but it's something that's going to come up a fair bit for us in this unit. So you want to get comfortable with it and be able to figure this out. So now I've got the expanded form of the function and factored form of the function. I've got expanded form of the derivative and factored form of the derivative. You may want both of all the different functions that you're going to have. Sometimes expanded form is useful for different things, which we'll see when. Sometimes factored form is useful, is easier to use. I like to do all this work at the beginning and get it all out of the way so I've got all my completed forms done before I start getting into the rest of the details. And then I always start with intercepts. What's the y-intercept? So if I set x equal to 0 in the original function, then I get 0. 0 input, I get 0 output. So my y-intercept is 0. What's my x-intercept? That's when this x to the 2/3 times x to the 4/3 minus 3 equals 0. If you don't have to write this out and do it this way, you're probably better off, right? Not having to write this whole thing out and solve it, just being able to get it by inspection. So what are they?
0 plus or minus 3.
X equals 0, or I could do, x to the 2/3 equals 0, which means x equals 0. And x to the 4/3 equals positive 3. Now how do I solve this? What were we going to say?
Plus or minus cube root?
Close.
Or the cube 3?
Close. This here?
Do you want the final answer or like how you do it?
Yeah, tell me what to do.
So would you just cube both sides and then do the 4th root of 27? Plus or minus?
Yeah. Fourth root of 27. 2.28. Questions about that? So again, that's a little strange, but that's just something that you have to get used to. Okay, asymptotes. None. But we're gonna write that anyway. We're gonna write it out because starting tomorrow we're gonna have asymptotes, and it's just a good thing to think of every single time. But when you have polynomials or these kinds where they don't have a denominator, you're not gonna have anywhere where you're dividing by zero, so you're not gonna have an asymptote. Okay, so I would take this is how I would do it. Take my function, factor it. I would use this one to do the derivative like we did yesterday. I would not use factored form for the derivative because that's product rule, that's harder. Okay, get my derivative, factor that, have all of that done, do my intercepts, do my asymptotes, and then go and do my first derivative chart. We've already done that. That's the order that I would do it. And then once you have all that done, you start putting it together. Okay, so my intercepts are negative 2.28. I'm going to do it off this side a little bit. 0 and positive 2.28. From all the work we did yesterday, I've got two turning point mins, and they're symmetrical, -1, -2, and +1, -2. And I've got a cusp max at 0, 0. Also, it's decreasing here. Then it increases, then it decreases, then it increases. In some cases, that may help you think about the end behavior. So if I'm decreasing, I'm coming down through that. Local minimum, turning point minimum. Cusp maximum, turning point minimum, and then increasing in the end. And then this is what I do to simplify things a little bit. I think it simplifies things. I name these points A, B, C. In fact, I'm going to do it in a different color so it stands out a little bit. You don't have to do it in a different color. A, B, C, A, B, C. Otherwise, sometimes what people do is they actually label them with the ordered pair. But I like to do it like this. I also show it on the axes. Any questions? So that's a graph with a cusp. It's okay? Okay. Ready to move on? Complete a fully labeled sketch of the function below showing all intercepts, asymptotes, classified critical points, and end behavior. You don't necessarily have to write down the instructions, at least not right now, but you want to start with the function. We're going to get into this. Sketching is easy when somebody else sketches it for you, and you can look at what theirs looks like and then make yours obviously look the same if you're just copying the note. But if you remember from last semester, it's all about painting a picture in your mind. And now we're doing some different graphs because we have cusps and vertical tangents and stuff. We don't do those in MHF. Otherwise, a lot of these are going to look similar to ones we've done before. But they have more detail because I can label maxes and mins and twists and stuff like that, right, with their actual point where they occur. What do you think we're going to do first? So the one part of this is doing all the work and organizing it and obviously doing it correctly and all that good stuff. That's one side of this. The other side of this is being able to put all the pieces together and form a proper sketch. So what do we do first? I'm going to factor it first if that's okay, but yep, then that's the next thing we're going to do. So how do I factor this? Yeah, x to the x cubed. Oops. X squared minus 15. Okay, now I'm going to take the derivative. And I'm going back to the original polynomial form to take the derivative because that's much easier than doing product rule. Then what do I do with this? Factor it. Now what do I do? Factor it. I think it's a good habit to get all of this out of the way before moving on. Okay, intercepts. Y-intercept is when x is 0, so I just sub x into the original function, f at 0. So it's 0. If I have a y-intercept of 0, I have an x-intercept of 0. Obviously, looking at factored form now. So I've got intercepts of 0 and, good, plus minus root 15. That looks like about 3.9. So negative 3.90 and positive 3.9. That makes sense. Almost 4. Asymptotes. None. Just a polynomial. We've already taken the derivative. We've already got all of that done, so I can just go straight into getting my chart set up. For critical values, f prime at x exists for all x. Again, using my understanding of what kind of a function it is, there's no reason for it not to exist, so it exists everywhere. And you have to state that like we did before, okay? F prime at x equals 0 at x equals what? 0? And plus minus 2, 3, negative 3, 0, and positive 3. I like to do them in order just because that's how I'm going to graph them, but you don't have to do that, obviously. Okay? Now what? Not quite. Yeah, our chart, right? Our first derivative chart. So organize this stuff into a table. Very good. So x less than negative 3 at negative 3. Negative 3 less than x less than 0 at 0. 0 to 3. 3 and x greater than 3. This is where we're subbing values in. I'm just writing this down because I can't see it on my screen. There's no reason for you to write that down again. So, pick some big negative number. When I put it into 5x squared, the x squares it, so it's positive. Then when I put it into the other two brackets, they're both going to be negative. So I've got two negatives, which means overall I'm positive. Then I'm 0. Put in negative 2. Again, the 5x squared part is positive. But negative 2 plus 3 is positive. Negative 2 minus 3 is negative. So this is negative. Same thing if I put in positive 2. I get 1 negative. People get in the habit of it just flipping back and forth. But that's not what happens in this case, so be careful of relying on that. You have to do the testing. If you, I'm not going to actually do the testing out loud every single time because I'm going to assume that that's something that you can follow and you can do on your own. You should know how to do it. It's the same every time. If I ever do it differently or have a trick, I'll definitely share it. But otherwise, I'm going to kind of skip through some of that in order to save time. Okay, so we can talk about more interesting things. So increasing horizontal tangent line, decreasing horizontal tangent line, increasing, nope, decreasing, whoops. Increasing, 0, decreasing is a turning point max. Decreasing, then 0, then decreasing is? Twist. Decreasing, 0, and then continues to decrease. That's your twist. It's not changing. Okay. And then this one is decreasing, horizontal tangent, increasing. Draw it out if you have to, right? Like how I was doing this. So this one was increasing, 0, decreasing. This one's decreasing, 0, increasing. This one's decreasing, 0, decreasing. Look, it's a twist, right? It shows you what it is. Okay. So if you have to off to the side, use those little sketches. So this one is a turning point min. Once again, you have to decide what's most efficient. And as you're practicing, hopefully you're thinking about that. And you're going to try it different ways. Does it make sense? I got to find 3 points at negative 3, 0. Well, the 0 one is going to be easy. Because if I already know that my intercept is 0, 0. I already know that. So I've got that one. Should I punch it into this or should I punch it into that? Which one's faster? Or if you are programming your calculator, x to the 5th minus 15x to the cubed equals, and I put in negative 3, and I get 162, and I put in positive 3, and that wasn't right. What did I do wrong? Oh, I have to hit equals. Negative 162, right? So, I was pretty fast. Maybe faster than typing them each in, I don't know. If I had to do a bunch more values, definitely it would save me some time. So this one was negative 3 and positive 162. This one's 0, 0. And this one was positive 3, negative 162. A, B, C. Can anybody visualize this thing yet? Sort of in your mind what it's going to look like? And just like MHF, if you get something on the wrong side of something else, boy, that's going to cause a problem. What's the other thing that we know about this we haven't talked about, and I'm not going to write it down, but I want to think about? Straight out of MHF. Thank you very much. Degree 5 positive leading coefficient. So I know the end behavior from that. And I'm just going to, I don't have to write it down, but I'm showing it in the graph, right? Obviously showing the end behavior. So I've got an x-intercept at negative 3.9. I'm going to come out here a little bit. I've got another x-intercept at positive 3.9. My end behavior is starting down in this quadrant and ending up in that quadrant. Ready? Come up here. Turning point max. Twist. It's decreasing. Twists, still decreasing. Turning point min. And then finishes in that quadrant. There's point A, point B, point C. I'm going to label these. Any questions? We're going to do one more. Everybody okay? Once again, we started with factoring, taking the derivative, factoring that. So I've got all the different forms that I need. Find the intercepts using factored form of the original function. Asymptotes, we'll talk more about those tomorrow. Then I get into the first derivative chart. I state where it does not exist and where it's equal to 0. Put all those critical values into my first derivative chart. Complete the chart. Classify the critical points. Find what the actual points are. And then start putting it all together into my sketch. Same instructions as last time. You don't have to copy it all down again. Another polynomial function. See if you can get the first couple of steps started. Did everybody start with that? I haven't done this one before. Mrs. Graham said it was a good one and we'd have time to do it and it would be a good one to do. So I'm seeing it for the first time just like you are. What now?
You take the derivative of the original.
Okay, sounds good. Keep going. Okay, so that's what I got so far. Now, I common factored out 10x squared, and then I factored the trinomial that was left. Why didn't we do that before? Why didn't we do that with the original function? How come we didn't finish factoring this? Sarah? How do you know? Very nice. B squared minus 4ac, good idea. Efficiency. Checked that value. What was it? Do you remember? 105. Anybody else check it? 105. Okay. Intercepts. What's the y-intercept? 0, thank you. X-intercept? Thank you very much. B squared minus 4ac showed it's not factorable, but there are solutions. What does that mean? There are x-intercepts. So do you have to use quadratic? Of course you do. You got to find those intercepts. Absolutely. So my intercepts are 0 and 5 plus or minus the square root of 105 over 4. So what does that work out to? Negative 1.30 and 3.8. Is that what other people got? Anybody else try that? Yes? Awesome. So we're sketching. So like, I don't need 2 decimal places. I mean, you know, I'm not gonna round to the nearest whole number. I'm gonna keep 1 decimal place. But what, like 3.81 or 3.82 isn't gonna make a difference in your sketch. You know what I mean? So yeah, 1 decimal place is good enough. Sometimes you might see people showing 2. Like it doesn't really matter, but it won't say in the question to 2 decimal place. Like it won't say that. It's just sketch. Asymptotes. Once again, this is degree 5. So none. Degree 5 polynomial, sorry. So polynomials don't have asymptotes. All right, first derivative chart. Whoops. Exists everywhere. Always got to make that statement. So now going to factored form of my derivative at -1, 0, and +3. Everybody okay? Okay, I'm going to let you do the chart. Okay, that's what I got so far. Let me know what you think.
One question. When it's a horizontal tangent line that's decreasing, can you just write decreasing right beside it? And it just writes points, or do you just state that horizontal tangent line decreasing?
Say that again?
So now when it's a negative, right?
Yep.
So it's a horizontal tangent line.
Twist.
Oh, it's a twist, okay.
That's the same as the last one. It's decreasing, then 0, then decreasing, so it's a twist. This chart looks a lot like the last one. Like all these two columns, the two second columns are the same. Another one with a twist in the middle and a max and a min. So there's my 3 points, ABC. And I'm going to draw this somewhat to scale. So I have x-intercepts at negative 1.3. Zero and 3.8. You know, you could, for one like this, try to draw it first and then label the intercepts after. Labeling the intercepts might make it difficult to force the curve to look natural and smooth and make it through that intercept. So I don't know, I might be shooting myself in the foot here by doing this. Let's see. So again, this was degree 5. Same end behavior as the last one because it was a positive leading coefficient. And my max is at negative 1.3, so fairly close to my x-intercept. So I'm going to come around, max, twist, then it goes way down. Not bad. So I've got my max at negative 1.3, my min at positive 3, negative 189. And labeling my 3 points A, B, C. They're not always symmetrical like the first two that we looked at.